13.75 billion years ago, the universe began. A number derived with remarkable precision. But how do we know? Before 380,000 years after the Big Bang, the universe was so hot that atoms couldn't form. Instead, it was a soup of electrically charged particles, too volatile for electrons to orbit atomic nuclei. During this time, the universe was opaque to light, resembling a vast, glowing star. Now imagine this. What if the universe existed long before the Big Bang? This might sound like science fiction, but acclaimed physicist Brian Cox explores this mind-bending idea with enthusiasm. A universe before the Big Bang. The conventional understanding is that the Big Bang created the universe, as explained by Einstein's theories. This is textbook cosmology. However, new theories suggest there was a phase before the Big Bang, known as inflation. During inflation, the universe expanded exponentially fast, doubling and redoubling in size in fractions of a second. Starting from a space smaller than an atom, it grew larger than the entire observable universe with its 350 billion galaxies in less than a millionth of a second. When inflation ended, the energy driving this expansion was released into space, heating it and creating the particles that form stars, galaxies, and everything we see today. This process is what we traditionally call the Big Bang. What started inflation? The critical question remains. What initiated inflation and why did it stop? While we don't have definitive answers, some theories suggest there may be more than one universe, possibly an infinite number. This idea, though speculative, is grounded in science and opens the door to the concept of a multiverse. If multiple universes exist, each could have different laws of nature. For example, the strength of gravity or the speed of light might vary. Our universe, perfectly tuned for life, exists because we are here to observe it, a perspective supported by the anthropic principle. The Penrose hypothesis. Universes before our own. Nobel Prize-winning physicist Sir Roger Penrose adds another layer to this discussion with his theory of conformal cyclic cosmology, CCC. Penrose suggests that our universe is just one in an infinite series of universes, each born from the remnants of a previous one. According to this model, the universe undergoes cycles of creation and destruction over unimaginable timescales. This means time itself may have no beginning or end. Instead of an eternal existence, Penrose envisions a series of cosmic rebirths, a concept that challenges traditional ideas of space and time. Evidence from the James Webb Space Telescope. Recent discoveries from the James Webb Space Telescope, JWST, have sparked renewed interest in Penrose's CCC theory. Webb has identified galaxies and black holes so ancient they challenge the Big Bang timeline. For instance, Webb detected 16 galaxies that appear to have existed shortly after the Big Bang, along with 6 massive black holes, each over 1 billion times the mass of the Sun, just a few 100 million years after the universe's formation. One galaxy, strikingly similar to the Milky Way, raises significant questions. Conventional cosmology holds that spiral galaxies like the Milky Way require billions of years to form. Yet this galaxy, existing only 2 billion years after the Big Bang, appears highly developed. Its level of complexity challenges the standard model and suggests the possibility of structures predating the Big Bang. The implications. Could the Milky Way itself be older than previously thought? Was it already traversing space in some form during the early universe? These questions are reshaping our understanding of cosmic history. The proximity of this galaxy, compared to other ancient objects identified by JWST, offers a unique advantage. Its relative closeness allows scientists to analyze its stars, compositions, and structures with greater precision. The data suggests this galaxy reached a level of maturity comparable to the Milky Way in an extraordinarily short time, further complicating established cosmological theories. Expanding the horizon. The discoveries of the James Webb Space Telescope are pushing the boundaries of our understanding, challenging traditional ideas about the universe's age and origins. Could our universe be part of an endless cycle of creation and destruction? Is the Milky Way far older than we think? While the idea of a multiverse or universes before the Big Bang remains speculative, it's a scientifically valid area of exploration. As our tools and understanding improve, The answers to these profound questions may redefine reality itself. The story of the universe is far from complete, and every discovery brings us closer to unraveling the mysteries of existence. The arrangement of universes and the mechanisms driving cosmic expansion can be understood through a remarkable aspect of physics: gravity's dual nature. While Newton's law of gravity describes it as purely attractive, Einstein's theory of general relativity reveals that under certain conditions, gravity can behave repulsively. Modern particle physics strongly supports this, suggesting that at extremely high energies, forms of matter exist that can generate this repulsive gravity, as permitted by general relativity. This concept forms the basis of cosmic inflation, the idea that the bang of the Big Bang was driven by this repulsive gravity. When inflation is considered as the mechanism behind the universe's birth, it predicts a universe that matches our observations. For instance, inflation explains the extraordinary uniformity of the cosmic microwave background radiation. Measurements show that its intensity varies by only 1 part in 100,000, a level of uniformity that the standard Big Bang model cannot account for without inflation. In the 1980s, researchers proposed that shortly after the Big Bang, a small region of space underwent rapid expansion driven by inflation. This period of inflation smoothed out initial irregularities, giving rise to the uniform universe we observe today. However, the theory of eternal inflation suggests that this process never completely stops. In some regions of space, inflation halts, creating bubble universes, while in others, it continues indefinitely, potentially generating an infinite number of universes with varying physical laws and constants. This framework forms the basis of the multiverse theory, a domain of continuous expansion and creation. Within this multiverse, bubble universes may interact, with inflation slowing overall. The multiverse can be imagined as a vast, dynamic realm of constant development, analogous to Earth as a thriving ecosystem with endless cycles of life and renewal. In this context, the concept of a cyclic universe emerges, emphasizing perpetual regeneration on a grand scale rather than a definitive beginning or end. Einstein's theory of relativity reshaped our understanding of spacetime as a four-dimensional continuum influenced by mass and energy. Despite deriving many scientific principles from this framework, crucial aspects of reality may remain beyond our grasp. Pushing the limits of our current understanding, scientists continue to seek a unified theory, a singular equation encompassing all forces and phenomena in the universe. Einstein pursued this unified field theory throughout his life, yet it remains elusive. Perhaps the challenge lies in our narrow focus. Just as one cannot fully describe a tree by examining a single leaf, attempting to decode the universe by studying its smallest components may overlook the broader picture. The deeper we probe into the subatomic realm, the more complex and perplexing our observations become. Similarly, even with telescopes like the James Webb Space Telescope capturing light that has traveled over 13 billion years across a 90 billion light-year expanse, our observations may represent just a grain of sand on an infinite cosmic shore. This raises profound questions. What role do black holes play in the universe's formation? Could they have been among the universe's earliest entities? Astrophysicist Neil deGrasse Tyson offers a compelling perspective, suggesting that not only are we part of the universe, but the universe is also within us. As humanity stands on the brink of answering some of its most fundamental questions, where the universe began, what brought it into existence, and whether we are part of a grand design or a cosmic accident, new discoveries may redefine our understanding. Tyson has proposed that the James Webb Space Telescope may have detected signs of black holes from a previous universe. If confirmed, this would suggest that our universe is part of an eternal cycle of cosmic rebirths. Such a revelation would necessitate a complete re-evaluation of the history of cosmology and our place within the vast, interconnected multiverse. A groundbreaking discovery sheds new light on the early universe, offering potential support for Roger Penrose's Conformal cyclic cosmology, CCC. Observations reveal a system formed billions of years ago with an estimated mass of 3.9 billion solar masses. While this is significantly larger than expected for galaxies of that era, it remains relatively small compared to the Milky Way. However, the focus of galaxy evolution in the early universe extends beyond mass, delving into the transformation of their shapes over billions of years through chaotic mergers and growth processes. This recent finding aligns intriguingly with CCC, a model proposing that the universe did not originate from a conventional Big Bang but instead emerged from a previous universe. According to Penrose, each universe begins with an event linked to a prior Big Bang. Unlike earlier cosmological theories that struggled to explain what existed before the Big Bang, ranging from the claim of nothing to the quantum physics suggestion of a quantum tapestry, CCC posits a cyclic universe. Penrose's theory proposes that all information about matter, stars, and galaxies from an earlier universe could transfer to the next cycle. Penrose's conformal cyclic cosmology explained. In CCC, the universe transitions through stages of death and rebirth. As vast black holes consume all matter, the universe reaches a state of complete equilibrium, where no measurable forces or matter remain. In this transition from cosmic death to a renewed state, the universe enters a phase resembling a spark of life, or scientifically, a fundamental law of cyclicity. Penrose suggests that the universe's properties at its end mirror those at the start of a new era. This idea emerged from Penrose's study of general relativity and quantum mechanics, fields often seen as contradictory. He identified key connections and inconsistencies, focusing on singularities and the cosmic microwave background, CMB. Penrose noted that the universe's initial state of exceptionally low entropy, reflected in the smoothness and order of the CMB, could provide clues about its large-scale structure. Black holes and the cyclic universe. Central to CCC are the residual traces of black holes within the cosmic microwave background. Penrose theorized that black holes from a previous universe could evaporate through radiation, leaving detectable imprints in the next cosmic cycle. Alternatively, some black holes might survive the transition, lending insight into how ultramassive black holes near the Big Bang could exist. If matter, stars, and galaxies transfer seamlessly between universes, it suggests accelerated growth of cosmic structures. This revelation supports Penrose's hypothesis, raising profound questions about the true nature of reality. Implications for cosmology and physics. CCC complements concepts like eternal inflation and the multiverse theory, challenging conventional perceptions of time, space, and the origins of the universe. Eternal inflation, as proposed by physicists such as Alan Guth and André Linde, describes a prequel to the Big Bang, providing a narrative of the universe's expansion before its visible formation. Together, these ideas offer a cohesive framework for understanding the cyclicity of the cosmos and the deeper fabric of existence. Penrose's theory, supported by recent discoveries, could redefine our understanding of the universe's origins, evolution, and ultimate fate, bridging gaps between cosmology and quantum physics while inspiring further exploration of time, space, and reality itself.